Okay. So the last video cut out due to a phone call. All right. We'll just finish up where we were. So 4,312 we realized equals 2 to the power of 3 times 7 to the power of 2 times 11. All right. From there, we know 2 to the power of 3 is 8 times 49 times 11, and that equals 4,312. All right, exactly the number that we're looking for. Okay, so the check works. All right. Okay. So that was the factorization, the factor tree. All right, method that we use. All right, and now we're just gonna follow up with number 7. All right, the quotient remainder theorem. The acronym that we use for the quotient remainder theorem is QRT. Okay? So this theorem states for any integer n positive number D divisor, there exists unique numbers Q, which is our quotient, and R, which is our remainder, such that n equals dq plus r, 0 less than or equal to r less than d. Okay? That's the formal definition that we're going to use for this. Okay? Now let's go through an example. Okay? We're going to use example. All right. This is really a simple idea of long division. All right. So when we're going through, this is very similar to long division. We'll put n equals to 7. Okay. And d equals 2. All right. So now replacing and substituting in these values, 7 equals 2 times q plus r. All right. Now, in order to find this, or this is a little bit of a simple one, just an example. All right, but in order to find this here, we could do some long division. So we have our divisor, 2. Okay, this is 2 is our divisor. Our dividend is 7. All right. Then we're gonna say, all right, 2 goes into 7 3 times. Minus 6 here equals 1. Okay, so then we're going to bring this 1 up for a remainder 1. So we're going to end by saying 7 equals 2 times 3 plus 1. All right, and that follows all the rules that we have laid out here. Okay, n is an integer, 2 is a positive number, 3 is a unique number, and so is 1. All right, 1 is greater than 0, okay, and 1 is less than 2. All right, let's go through one more example just to make sure. So now we have, let's put n equals 13, d equals 5. Okay, so again, we're just going to plug it in, substitute in these values, 5 times q plus r, okay. Setting up our long division, 13 is going to be the dividend, 5 is the divisor, 5 goes into 13 twice, subtract the 10, okay, we're going to get 3, remainder 3. So 13 equals 5 times 3 times 2 plus 3. Okay? And again, our remainder is greater than 0. Okay? And our divisor is greater than our remainder 3. Okay? So these both work. Oh, that was a check. Okay? Check. Check. And there we go. We have the quotient remainder theorem. Okay, so we'll just go through it again one more time. For any integer n, positive number d, the divisor, there exists unique numbers q, which is the quotient, and r, which is the remainder, such that n equals dq plus r, and 0 is less than or equal to r, less than d. Our two examples, all right, using the simple idea of a long division for this kind of problem, we'll see, okay, if 2 doesn't divide 7 cleanly, we're going to get a remainder, okay, and then we could plug it into this formal definition that we have, all right, and it all works out, all right.